Hello and welcome to the shed, and this is a polyfuse, and I've been using polyfuses to protect my electronics in the shed. Now they are different to fuses, and I shall go through with you what the differences, what they are and what the differences are compared to fuses. Yeah, I think I said that right. So what I have here is an electronic load, a polyfuse and a meter measuring the voltage across the polyfuse. I have 5 volts coming in here, and you can see it reads 5 volts, 4.98, 4.9. It is roughly the same, and it's set to 200 milliamps. This is a 1.2 amp polyfuse. So as I increase the current, so I'll turn it on, and then I'll start increasing the current. I'll put my hand here so you can see the dial. As I increase the current, you can see the voltage across the polyfuse is increasing, and by using Ohm's law, you can calculate what the resistance of the polyfuse is, which I shall put here somewhere. So as I increase the current, you'll see the resistance of this will increase. So increasing the current, and you see the voltage is drop across it is increasing, and this is because this is actually heating up. So it's a ceramic device, and it heats up, and as it heats up, the resistance increases, and that's how it protects your circuit. So we get to 1.2 amps, and you see the voltage is increasing rapidly now. The voltage drop here is increasing rapidly. So as we go beyond that 1.2 amps, let's go to 1.5. This is where a polyfuse is different to a fuse. A normal fuse would just blow and open the circuit. So for higher current situations, it won't protect necessarily from that. Well, it will protect from overcurrent situations, but it won't protect for short pulses. There you go, it's tripped. What's happened there? Oh, for some reason my meter went into resistance, and I don't really know why, but there you go. So it hasn't tripped yet, but the voltage is steadily increasing. As I put a high current load on it, you see here the voltage here is also dropped. And you'll get to a point where that will start heating up rapidly, and it will go open circuit. Well, not open circuit, it will go very high resistance. We're talking kilo ohms resistance. So you come up to a volt drop. See that's rapid. See how quickly that right. So that's tripped now. So that went up really quickly, and it's now got the full current across it, or full voltage across it. Yeah, that is really hot to touch. I think what I should do is see if I get a thermocouple, and I can measure the temperature as it increases, as the current increases. So that's now open circuit. Well, it's not open circuit. We can work out the current, the resistance of it. So that's how much voltage you've got going in there, and that's open circuit. So if I disconnect the load, moves across it, and then we put this onto resistance. See, already it's recovered. So I put that back onto voltage, and we'll turn this down, reconnect the load. Yeah, voltage is, so that's now recovered. So again, the good thing with polyfuses is they're resettable. So even though you had an overcurrent situation, this has cooled down, gone back to low resistance, and is now powering the circuit again. Now as I increase the current, see the voltage drop across the polyfuses going up. If I left this for long enough, this would eventually trip. That would eventually get hot enough and go open circuit again. But I'm sure you don't want to watch that in real time because it'd be pretty boring. So I'm just going to put the current up to accelerate it. 0.9. So you can see how quickly it's going up. It's gone open circuit. If I open this up, put this onto resistance, again it's recovered instantly. I kind of expected it to hold its temperature for a bit longer than that, but it hasn't. So you see how quickly they recover. Turn the current on this back down. And it's conducting again. So the advantages of a polyfuse are they are resettable. You won't have to replace them. The disadvantage is as they get older and as they trip more, they become more prone to tripping at lower temperatures. And they don't instantaneously blow. So, for instance, if you had a dead short, there'll be a period of time when it is still passing current before this gets hot enough to actually open the circuit. Plus, these only go high resistance, so there will always be trickle current going through it to maintain its tripped state. But what I'll do, I'll see if I can find a thermocouple and we'll measure the temperature as it trips. Right, we'll try this. This temperature here is being a bit funny at the moment, so I'm not sure if this is going to work, but I'll give it a go. So we're currently drawing 900 milliamps. I'm going to increase the current and we should see the temperature starts to rise, which it is. So we've got 60 degrees there. And again, the temperature's been a bit odd, so I'm not 100% sure this temperature reading is going to be accurate. 50, 60 degrees sounds, say it's tripped now, so that's tripped. 70, 80 degrees does sound about right for this. So that could be right. But basically, as the temperature goes up, the resistance increases till it reaches a threshold and it suddenly shoots up the resistance. So, and then we should maintain that temperature. As I reduce the current, that temperature will drop and the resistance will go back again. Or the resistance will drop again. He says. We'll take the load off. There you go, you can see the temperature dropping. And now if I put the load back on again, the resistance is in the lower part of the threshold. And the temperature's still dropping because we're under that 1.2 cutoff voltage. Cool. Well, I hope that's kind of helped explain thermistors. If there's any more tests you want me to do, just leave a comment. And thank you, and I'll see you later. Right, bye.